Next up, we're just going to have a quick aside about initial conditions. Now, what I've been doing in the last couple examples is the thing that I think most students will like to do, which is you integrate everything, you have a constant, you plug in some numbers, and you solve that constant algebraically. But when I wrote down these steps way back at the start of discussing separable equations, I said that there could be like some tricks to how you use the initial conditions and solve for y and all that. And so I'm going to go ahead and address that using the same example right now. So to solve the same problem as we were looking at before, we can use definite integrals to include initial conditions from the start. So we're going to look at our same example again, where we had that dt is k times t minus 70, and t of 0 equals 300, just because it's familiar to us and we're discussing something new, so it helps to use that thing again. And we had gotten it into the form dt over t minus 70 is equal to k dt, and then we integrated it. And last time we integrated it and had unknown constants. But this time, what I'm going to do is I'm going to make these definite integrals. And the way I'm going to do that is I'm going to remember that I was given initial conditions on lower bounds. Sort of the first temperature that I ever consider is 300. The first time that I ever consider is 0. So importantly, you need to make sure they match the integral. So my integral on the right-hand side is with respect to time. That's why I plugged in my time temperature. My integral on the left-hand side is with respect to temperature. That's why I plugged in the temperature initial condition of 300. I'm going to erase all those lines so they're not cluttering up the space. And then just use the variable itself on the upper bound. So sort of I want to end at some temperature and some time. Sometimes this bothers people, so you can go ahead and use like placeholder variables on the inside if that is unpleasant for you to look at. Like that. And so what you're going to get is a definite integral that you can solve. So just real quick, you can skip using placeholders if you find that unpleasant. And I didn't write before, but put the variables on upper bounds. Okay, so that's how you set up a definite integral for this problem. And then from here, you just solve it. So I've got the natural log of s minus 70 evaluated from 300 to t is equal to k times s evaluated from 0 to t. And so that's evaluating the definite integral. And we're going to continue that. When I plug in those bounds, I'm going to get natural log of t minus 70 minus natural log of 300 minus 70 is equal to k times t minus k times 0. So I've got natural log of, t minus 70 is equal to natural log of 300. 300 minus 70 is just 230 plus kt. All of this here, I'm just going to be solving for capital T. So I take the exponential of both sides. I get t minus 70 is equal to e to the natural log of 230 plus kt, which is just 230 e to the kt. Or t is equal to 70 plus 230 e to the kt, which is the same solution we got by back here. By integrating the whole thing, having an unknown constant, and then plugging in our initial conditions later. All we did here was we plugged in our initial conditions at the start, took a definite integral instead of one with an unknown constant, and then we never had to solve that algebra problem because it was kind of built into solving for t in that final step. And so whichever way you prefer to do problems, you're welcome to. There will be some problems that are easier to represent this way, some that it's, more effort. So I'm just going to recap real quick. During the evaluation of the definite integral is when you end up solving the IVP using this method. So you can pick the method that you prefer. You need initial conditions for this to work. But it's helpful when the integral can't actually be solved. So kind of in general, if your integral can be solved and you have initial conditions, you can use either approach. If you don't have initial conditions, you're going to want to use the first approach. If the integral can't be solved, you're going to want to use this approach. And in the next video, we're going to do an example where that's what happens so that you can kind of see why this is the case. So go ahead and watch that one whenever